Just a quick question about the homework.
Yeah.
So you told us last class you want us to leave it in positive conventions for our answers, and then we use a negative or positive sign consistently, or do you want us to only use positive signs and then just indicate which direction the internal forces are going? Like, would you rather me put like like just an example, like not the answer, but like if I have if I got a negative answer for a moment, do I just leave it negative or do I say that
Follow. So I want to clarify here. The content in my statics review does not contradict to of what you learn from statics. Is consistent because I do use a statics textbook before I teach this class. So this is consistent with your statics definition of where the internal force should be. So let's say if in this situation, you should have a positive value, no matter which section you choose. If it's compression, you should have a negative value. It's not that you have a positive value and then you indicate it's tension, or you have positive value and okay, this is the magnitude, but it's compression. No. Whenever for normal force, when you calculate the positive value, it should be tension. And if you calculate negative value, it should be compressive. For the bending, if we define this is a positive bending, then this one, they all should be positive. If the bending is in this way, no matter you take left or right section, your bending moment, internal bending moment, you calculate should be a negative value. So the positive and negative value itself already explained. It is tension compression, bending upward or bending downward, or shear in this way, or shear in this way. So the value with the sign already explained everything.
okay, thank you.
Welcome. Any other question? So I can do some screenshot of the statics textbook to prove that this is indeed consistent with your statics textbook. This is absolutely not something new or some like special way that I prefer to use. No, this is consistent with statics. This is consistent with mechanical materials. So, and also I want to expand a little bit since I feel like many of you are still confused, like why we do need to define positive surface, negative surface, and have this sign convention of the internal force. Let's say when we define tension as positive for this 1D bar situation with only actual force applied, let's say if somehow some of you make a mistake. Let's say, okay, on this surface, such this define this is the positive internal normal force. So what happened is that, okay, you do the force equilibrium, and then you have the internal force plus this one, external applied force, and equal to 0. And you calculate the normal force, internal normal force. Here you get a negative number. Makes sense not? Let's write it this way. Let's say somehow, if you mistakenly consider on this surface, your normal force is in this direction. And how to write the force equilibrium equation? You have the N plus internal normal force equal to 0. Let's say put the internal force here. And this is the external applied force, right? So now your Ni equal to negative external applied force. So if you don't follow this sign convention, somehow you will get a negative value. So what will happen is that, okay, for checking the internal force at the same point, I can either take a left section and right section for calculation. But if I take the left section, I get a positive value because in this one, I obviously have, let's say this is internal, this is external. So this one equal to 0. Sorry, one is this one is in the negative x-axis. So now the internal force equal to NE. Now you see the problem. In the left side, I have internal force equal to positive NE, right? In the right, if I chose right section, the CB section, the internal force equal to negative NE. Then the confusing part becomes, wait, this is tension. Why I use the left side and use the right side for the calculation? I should always get positive value, but here I get positive value only when I use the left section and get negative value when I use right section. This is why we always to be very clear of the sign convention. Only in this way, let's say this is on the positive surface, this is on negative surface. We follow this sign convention. Now we have everything correct. So no matter I choose left side, right side, I always get a positive value, and it always represent is the tension situation. And the same thing for bending, same thing for the shear. No matter I choose, so let's say you choose the left side, your friend chooses the right side, it doesn't matter. As long as it's bending upward, you and your friend should always get the positive value. It's not that both you and your friend are doing correct, but just someone get positive value and someone get negative value, and then you explain, oh, why I get a negative value, why I get a positive value. It's gonna be a whole mess. The whole thing here is that we made it consistent, and once you get a value with a sign, we know what it means. Is this clear or not? Let's expand to another question. So let's say in the sign convention, in the internal force, we always emphasize the sign convention. So you can set everything correct. And in the equilibrium equation, some students ask in the last class, like, okay, since you already defined like the positive, negative for the internal force, why you put it in the equilibrium equation, you always follow the coordinates. Let's think in this way. Whenever you put a force in the equilibrium equation, let's say use this one as a example, or it doesn't matter. I can use either case. So let's say for this bar, this horizontal bar, AC section, when I cut through here, this point, on the, let's say this is A, B, C, D. I use D point. That's D point here. For the AD, when I consider the whole AC section, and I cut through this point, and on this, when I cut through this, I generate two surfaces. One is the surface point towards positive X. One is the surface on the right side point toward negative surface. So the positive and surface negative surface. And when we consider the, please mute the microphone. Thank you. When we consider entire section, yes, of course, there are the internal force. But when we do the free body diagram of a single section, no matter it's the AE section or it's the EC section, for this section itself, all the force here, we can consider they are the externally applied force to this specific section. Make sense or not? So now this internal force, when we consider the entire section, now becomes the external applied force applied from the CD section to AD section. So now we are writing the equilibrium equation of the AE section, and whatever force we put on the AE section, they all consider external applied force for the AE section. That's why when we put the force equilibrium equation, oh, we said, okay, this is a downward. In terms of the internal force before we do the cut, this is considered as a positive internal force on the positive shear force on the positive surface. But when we put it in the equilibrium equation, we do need to put a negative sign, because now everything, when we put the equilibrium equation, everything follows the coordinates. As long as it's in the positive y direction, it should be positive value. As long as it's negative y direction, it should be negative value. It doesn't matter if it's from reaction force. It doesn't matter if it's from the internal force. It doesn't matter. It's like external applied force. So specifically for this section, everything applied on this AE section, they consider the external applied force to the AE section. Or you can consider the force here, we consider like before we do the cut, or before, or when we consider entire section AC. Yes, these are the positive internal force. But after we separate the AD section of the entire AC beam. Now, the force here we can consider is the force applied by the CD to the AE. That's why when we consider AE specifically, it's considered as external applied force. So I hope this one help you like understand why it's very important to define the sign convention of the internal force. Why when we do the equilibrium equation, everything follow the coordinates. Is this clear? Any question related to this part? I can post a screenshot of statics later to show you that this is consistent with the static textbook. This is not something new. And also, this is the screenshot from the statics about the two force body, and this explains why when a structure, no matter it's a strained structure or it's this L shape or any kind of shape or any shape, as long as there's only two force applied at two ends, the two force should be the line of action should be the connection of these two free end, and also opposite side. It's if it's tensile this direction, if the compressive this direction. So this is a two force member. Be very clear about two force member, because for two force member, the force is one single unknown. I emphasize here because for this problem, if you didn't realize that this is two force member, and somehow for the reaction force you put AX, AY, for the reaction force DX, DY, there's no way you can solve the problem, because now you have four unknowns and you only have three equations: force in X, force in Y, moment equilibrium equation. Four unknowns, there's no way you can solve the problem. The only way you can solve the problem is that you need to realize this is a two force member. So instead of two unknown at D is only one unknown, because the line of action of the force should be in the CB direction. So now it becomes 1, 2, 3. And you have three equations, three unknowns. You can solve the problem. So that's why it's very important. I got a question during the office. I was asking about like they confused about this part. So this is screenshot from textbook and explained. If it's not, let's say, for example, if it's situation like this, then it will generate rotating moment. As long as it's not in the same line of action, it will generate a rotation, and there's no way it can stay in equilibrium. The only way to stay in equilibrium for the two force member is they have the same magnitude, they're in the same line of action, they're in the opposite direction. Now let's check the example 3. The internal force at point G point here, two dimension are given. So what are the major steps for calculating the internal force at point G?
Finding the reaction forces.
Yes. Do we need to find all the reaction force at C and E, or only part of them is necessary? Do we need to find all three reaction, or only part of it?
I'm gonna take a guess. I don't think C's reaction forces affect the internal forces at G.
Yes. So let's do it this way. Yes, you are correct. Thank you. We have three unknowns here. We have the reaction force. Of course, this is two force members, so it's the force, the line position either this way or this way. So this is one unknown. Here we have two unknowns, X and Y, right? So of course you can solve for all three reaction force, but it just waste of your time, especially in the exam, especially if you are solving a very complicated project in your senior class. A lot of times only focus on the information that you need to have. And for the information, for example, this is really unnecessary to solve the reaction force here. Let's do it this way. Let's say if we want to find internal force at point G, there are two ways. Either I take this half or I take this half. And of course, by checking this picture, we know that probably take this half is easier for our calculation. And for this section, AG section, of course, we need to calculate this force, right? Direction given, only one unknown. And for calculating this force, we can do the equilibrium of this joint. So if we know the BC force, of course, we can calculate this force on the generated in the AB section. So we're done. So now you can see that the thing we need to calculate here is first this one. And because of this one, we need to calculate this force. So only one reaction force is necessary. You can calculate the reaction force here, it's just a waste of time. It's not necessary. So let's start from calculating reaction force at point C. Well, as a structure engineer by inspection, you know that this force is pull the structure downwards. This force is also push downward. So you can kind of by inspection, you should know that the direction force applied by this pin joint to the C point should be in this direction, right? Make sense? And of course, it doesn't matter if you put in this direction and you will get negative value and you know that it should be in this direction. So let's say by inspection, we know that the force applied at C point is, let's put that CX here. Or I just use F BC. And we have this force, and we also have the X and Y at point E. So again, doesn't matter, but let's put it here just in case if you guys confused like why I didn't put force here. Since we separate from the boundary condition, I put the EX, EY. Let's change this one to, since this is C point, CX. And of course, there is a distributive force in this section, and we can put equivalent concentrated force. So what is the equivalent concentrated force? I should put it in the BD section. What is the magnitude? Where's the location?
1,800, 2 feet from D.
Then it 900?
Yeah, 900. Thank you. So it should be 3 times 6, 2, right? So it should be the area of this triangle. And the location be the centroid of this area, which is 1/3 to this side. So let's put the equivalent force. Not skip any steps. Let's put this one here. And this distance is 4. If the only goal is to calculate the CX, instead of having 3 equations, I think 1 equation should be enough. What equation should we do? We can have force in the X, force in the Y, moment about a point to solve for the all 3 unknowns. But since now we only need to solve CX. Yes, moment about E. Yes, thank you. So just 1 equation moment about E is enough for solving CX. And the moment about E, first, this one will generate a counterclockwise. And the moment arm, this one is 10. And then we have this equivalent concentrated force also generate a counterclockwise moment about point E. This is the magnitude of the equivalent concentrated force. And the moment arm is 4. And of course, we have one more. This one will generate a clockwise, so it's negative. C. X. And the moment arm is this dimension, so 3. This should be equal to 0, way down. And Cx equal to positive. So we know that our first assumption of the direction of Cx is correct. Why does no Cy force? Again, 2 force member. CB is 2 force member. It cannot support any force that's not in the x direction. Otherwise, it will rotate. Is E not a pin joint? E is pin joint. C is pin joint.
Is
E is
BD also a 2 force member as well?
2 force member, 2 force member, 2 force member.
Okay, that's what I thought. Thank you.
Yeah, you're welcome. This one is not 2 force member. That's why we need to have Cx, Cy, but Ex, Ey. Yes, E is a pin joint and E could rotate. You are correct. E, this is a pin joint. This is a pin joint. This is a pin joint. It can rotate here. It can rotate here. It can rotate here. There's no clamped boundary condition here. Which part is confusing? Did I answer your question? Okay. And of course, if this, let's say, remove this pin joint, if it's clamped, of course, when we do the internal force, we need to add a moment. But here, since it's a pin joint, there's no moment. It does not construct rotation, so there's no moment of reaction force. Now we're done.
I had a question.
Yeah.
For the other 2 force members, how come in our general free body diagram they don't affect the moment about E, like BD or BA?
Yes, great question. Great question. So again, let's back to the equilibrium equation, free body diagram equilibrium equation. We are doing the free body diagram of this entire structure. We are doing the free body for this entire structure. Force here, they are the internal force. I originally wrote this one as FBC, but I changed to CX because I don't want you guys confused, like, oh, why internal force here is considered, but here are not considered. No, actually, it's more clear to put in a way that this is a force applied by the wall C or pin joint C to CB section, even though they are the same magnitude. And since it's torsion, since it's tension is also same sign, it's all positive. But this is a reaction force applied by the pin joint to the whole structure. So this is considered, when we do the free body diagram of the entire structure, this is considered a reaction force. This is considered one of the external applied force. Now, all the force in here and here and here, they are the internal force. When we do the free body diagram of that section, it's all about the externally applied force applied on this section. And of course, let's consider in this way. If now I want to do a free body diagram of this one, we're not doing for this example problem, but let's say for some specific situation, I want to do the free body diagram only for the horizontal beam structure, AE section. Now we need to consider this force, and reaction here. Because for the AE beam, for the AE beam, we separate AE beam from the entire structure. The force generated in this AB section, in the BD section, they become the externally applied force to the AE beam. Make sense or not? Because now we are doing the free body diagram of the entire structure, all this becomes the internal force. And external applied force, as I said, reaction force is considered one type of the external applied force, right?
Yes, that makes sense. Thank you.
You're welcome. So any other question for this part? So now this is the first step. And as I said, to take this section, we also need to figure out this force generated by AB. So it's better to do a free body diagram and equation of the B point, joint B. So second step, free body diagram, equilibrium equation of at joint B. And again, since our goal is only calculate this one, we don't need to calculate the force here. Of course, two equation, force in X, force in Y, we can solve everything. But our goal is only calculate this one. Only one equation is enough. Which equation?
Force in the X.
Yes, thank you. Thank you. Force in the X direction. So let's make it clear. Say we already calculated this one. This one is already calculated in the first step. Let's put it as FCB is equal to CX because the force applied by the pin joint to the CB bar is equal to the force applied by this CB bar to the pin joint, to the joint B. And also we have this force, and you should expect in this direction. So this is, let's say, F AB. And dimension, the slope here. Here we have 4, here we have 3. So 3. And of course, we still put this one here, but we don't need to calculate. So this is FDB. We only need one equation, Fx equal to 0. So now we have FCB equal to 62 minus FAB times, since it's X component, this is the X component of the force in the AB section, bar AB. So now FAB equal to CBB in the opposite direction, CB in the opposite direction, since it's opposite of the wall. CB. Opposite of the wall. What do you mean by opposite of the wall? Let's be clear. The one I'm putting here is a reaction force. Reaction force, definition reaction force means that it's a force applied by the C to this bar. So if the reaction force, if the pin joint apply a force in this way, do you agree that the force applied by the CB bar to the joint B is also in this direction? And then pulling, let's say I'm the pin joint, I'm pulling this point. It should be the same that this CB bar also pulling the B joint in the positive X direction. Did I answer your question? Is it clear or? If it's still confusing, please ask. Otherwise, I don't know if I should continue or not. So now we are done with the force in the AB. Now the last step.
I have a question.
Yeah. Yes.
With
Sorry. I cannot hear you. I cannot hear you.
hello?
Yeah. Okay.
Sorry, my internet gave out. Why is it that we're only concerned, at least right now, with the X component for AB?
It's not, we are only concerned about the, as I said, when you take this section, you need to calculate the force applied by the AB to the beam AE, right? This is the
Yeah.
only one you need. You don't need this one. It's not, we only care about the X component. It's, we do the force equilibrium in the X direction, we can solve for the AB. And we AB for the next step. It's only we need the force in the X direction.
Got it. Thank you.
And of course, let's say I see very frequently in the exams, because some students they always, whenever they have the free body diagram of a certain structure, it's always three equations: two force net, force one moment, or one force equilibrium and two moment. It's always set calculate the whole thing, and end up like waste a lot of time. We only have 2 hours solving 4 problems in the exam, and I saw very frequently that they have force in X and force in Y, so extra 2 steps to calculate these 2 parts, and also have the force in the Y direction, actual equation to calculate BD. And in the end, you will see that you won't need any of this. So just I'm intentionally using this example to tell you that only solving the necessary information. Be very clear before you start calculating any problem. Be very clear what are the necessary information you need, and only focus on those information. This is not about being lazy. This is about being an engineer. You need to using the least amount of time to solve the problem. Now we have this cut section AG. And of course, we have the external power force 1500. We calculate since now we check this B joint, since we have the AB bar is pulling the B joint in this direction. So you should expect that for the AG section, the force should be in this direction. And the magnitude you already calculated is 7750. And what else? Internal force on this cutting surface, we have, this is a shear force VG. This is a normal force NG. This is a bending moment. And I want to emphasize again here is following the sign convention on a positive surface, normal force, bending moment, positive shear force. Why is AB a 2 force member? Because there's only 2 force applied. If it has. Okay, I guess let me explain it here. Let me explain here. 2 force member does not mean like literally only 2 force. It's about, let's say it's force applied at free end and there's no force applied in between. So even though at B point, you may consider, oh, this is force in this, force in this, and force in this, you consider, okay, at this one end, you already have several force. And this one end, you also have several force, like you don't know what the force applied from the A beam to this A point, and also we have external. So if you count in this force, yes, it's more than 2 force. But what I mean by 2 force is that all the force applied this free end, we can combine it. It should be 1 force, because everything in the end, it should be in the x direction. And the same thing here, all the force applied to B end, it should be in the x direction. So in the end, you may have like different force apply A, but if you have the combined force of all the external applied force at A, it should be in this direction, and same thing. So 2 force is really mean that the force only applied at 2 end, and there's nothing applied in between. That's 2 free end. This one is not 2 force member, is because there's a force applied at D point. Could we consider FDB, FDC as 1? What do you mean by FBD and FDC? FBD, FDC. What is it? FDC. FBD, FDB, and FBD as FDC. What is FDC? There's no structure
I'm sorry,
connected.
I was gonna unmute myself. That's me. I'm talking about as the forces at FBD and then to BC. Could we consider that as like one angle as to FD to C?
No,
No. Okay.
we don't have a bar connecting the and C point. These are two sections. Why is not in compression as in how do you know it's positive? Why is not in compression? Did you mean the AB part, section AB? The question about why it's not in compression, did you ask about the AB section?
No, I was talking about the last part you worked on.
This one?
Yeah,
Which one should be in compression?
like it's not in compression, correct? It's in tension.
You mean this force?
Well, the way that you drew the reaction forces, VG, NG, MG.
This is internal force. This is not reaction force. This is the internal force on the cutting surface.
But didn't you draw it in the way such that it's in tension? And all
No. Whenever we have a positive surface, we always put the internal force in this way.
Okay.
This is the internal force. Don't get confused. This is internal force. It's not reaction force. It's internal force. And whenever we have positive surface, which means that surface is pointing to the positive x direction, we always use this sign convention, put the force in this direction.
Okay.
If we get a positive value, it means that it's in tension. If we get a positive value in bending moment, we know it's bending this way. If we know the positive value and we know that it is shearing in this way. If we get negative value, we know that this structure is in compression.
Okay.
Right. Okay. Back here. This make it less confusing. Okay. Now for the equilibrium equation, this is the third step, free body diagram, and the equilibrium equation of the section AG. And of course, now here we need three equations because we do need to calculate ng, we do need to calculate mg, we do not have vg. So force in the x direction equal to 0. So of course we have the x component of this one. The ratio is given here. So we have this x component is in the positive x direction, so it's positive. And we have, of course, ng, internal force on the positive surface. So now we calculate ng equal to a negative value, which means that it's in compression. Force in the y direction equal to 0. And we have this component, we have the y component of this one, and then we have the Vg. So negative 15 since it's downward. And this component is upward, y component upward. So plus the y component we multiply by 3, 5. Vg downward. Everything follow coordinates. So moment. Well, you can do moment about A, you can do moment about G. You should get a correct answer no matter which point you choose. So let's choose point about A. So, and if you choose point about A, of course, these two forces we can just ignore. And this one does not, this one pass through the point A, so it does not cause any moment. So the only two component we consider is this one will generate a clockwise moment about E, and this one is a counterclockwise moment about A. Sorry, about A. So two components. 3, 1, 5, 0. Moment arm is 2. And mg is counterclockwise already. So we have 3, 6, 3. When we say ask about internal force, you do need to consider normal force, shear force, and bending moment. Yes, you always, whenever we say the internal force, it always consider 3, normal force, shear force, and bending moment. But of course, a lot of times some of them are calculate 0 because let's say for simple example, I have 1D bar, I have applied tension, and you cut through the certain point of the bar. Only normal force is non-zero. Bending moment is 0. Shear force is 0, right? But when you do the calculation for general situation, always consider we have 3 components for the internal force. Any other question?
I have a question. When we calculated the moment, do we not account for the force from FB? I mean from FAB?
This one pass through point A. We are taking moment about point A.
Oh yes, okay, that makes sense. Sorry.
It's okay. Yeah, this force pass through point A, this force pass through point A, this force pass through point A. The moment arm of these 3 forces are 0. Where can I find a homework in the files? Any other question? Any question about homework? Well, you guys calculate. Any question about statics part? If no, we are done with static review. I cannot spend too much time on this part, but if you really need any help, I'm always happy to talk to you during the office hour. Okay, wait a second. Let's switch to, I also post a file that is about the lecture 2, lecture stress. Yes. You can check the files and lecture note, and you should see this one. Yes, I can help check if your method, let's say if you have any question about a method, you can come to our office or to ask, but we don't check your final number to see if your final number is correct or not. We don't have solution. I can only, let's say when you solve the problem, you have any question, you have any confusion in terms of method, we are very happy to help, but we don't calculate the number for you, or we don't have the number for you to compare if your calculation is correct or not. So this is a very quick review of the statics. And as I said in the introduction part of this semester, statics is all about calculating the internal force. Like they ask you to calculate internal force, draw the shear force diagram, drawing the bending moment diagram. But it's all in terms of force. And we know that as structural engineer, the main goal is to verify a design is safe or not, or let's say to reach some safety factor goal, how to optimize the design. So in terms of determining a structure is safe or not, knowing the force is not enough. Knowing the internal force is not enough. Because as I said, if the force is really, really big, I can always make the dimension, the cross-section dimension, let's say if it's only tension compression applied, I can always make the cross-section dimension big enough to support that force, and it's still safe. And sometimes if the force is very small, I can always make a very thin structure to make it break, right? So for a structure, it's safe or fail, it does not determined by the force itself. Of course, calculating internal force is a very important and first step of the determining safe or not. But in the end, we should know the stress in the structure and then compare the maximum stress in structure with allowable strength of the material. Then we know it's safe or fail. So the main goal of mechanics material is to do some calculation, find the stress, not just stop at the internal force. Of course, statics is a very important foundation. I'm not saying that it's not important. It's a very important foundation class. So this is in the textbook chapter 1.2, I guess. I think the first section is review. And it's about the axial stress, shear stress, and bearing stress. So first, the definition of stress, you probably already learned from the different class you took before. So it's the internal force intensity. It's a force of area in general term. Let's start from the simplest one, the normal stress. We'll talk about the bending stress, shear stress later, and also bearing stress. But the simplest situation is the normal stress when it's a 1D bar situation and we have tensile compressive applied. So the normal stress we normally put as sigma, and the stress, since it's a force intensity, so it becomes the force of a cross-section area, and P, sorry, N, is the internal normal force. Some textbook use P, some textbook use N for the internal normal force. It's the same thing. Just want to clear here. Don't get confused when you read textbook. and A is a cross-section area. So in the 1D tension compressive situation, tensile compressive situation, we can kind of assume that the stress is uniform distributed over the cross-section. And of course, if you go to higher level class, you will see that when it's concentrated force applied at this end, at two ends, you should expect that there's some variation of the stress. It's higher at the location at a point where the concentrated force applied and lower to when it has a distance from the point where the concentrated force applied. So there's in real situation, there's some variation of the stress distribution. It's not uniform distribution. It's not the same amount of the entire cross section. But because this variation is very small, especially when you get into towards the middle section of the bar, the variation gets smaller and smaller. So as engineer, we're not scientists here. As engineer, we can safely assume that this normal stress is uniformly distributed of the entire cross section, and is equal to the normal force. This normal force is calculated from statics divided by cross section area. So and the unit, since it's force of area, if you use the SI unit, we have Newton per meter square, which is given at Pascal, and of course, this is a very small number. Just imagine you have 1 Newton force applied, uniform applied to a 1 meter square area. So normally we could use kilopascal equal to 1,000 Newton meter square. Megapascal, 10 to 6. Newton meter square. And of course, if you use the foot and inch, and also force, you use pound. So you have the PSI. Inch square. Similarly, we have the KSI. 1,000. And MSI. 10 to 6. And of course, the sign convention for this one is very easy because there's no confusion for tension compression. It's always tensile positive, compression negative for the stress. So we talk about the sign convention for internal force, always tensile positive, compressive, negative. Same thing here for the stress. Whenever you see a positive stress, it means tensile stress. Whenever you see a negative stress, it means compressive stress. So the sign convention is same as internal force. It's always positive. This is sign convention for stress. And it's always compressive. Negative. So this is the basic concept of the normal stress, which is simply situation for all different kind of stress and a sign convention. Now let's check the first example problem. So for this one, it's a design problem. So we have a 1D bar structure, 2 section, and the allowable stress is given. For both section, there are 150 megapascal, which means that if you have a stress, if the stress generated in a structure higher than 150 megapascal, it will fail. You need to design the smallest dimension D1, D2, how to calculate. How to figure out the D1 and D2, smallest D1, D2. Anyone?
Could you put the area in terms of diameter and then rearrange the equation with the forces?
Yes, yes. So basically, in the big picture, since we already gave this equation, so in the big picture is that we need to make sure that the maximum stress in each section is lower than allowable stress, right? So of course, diameter, well, area can be written as a function of diameter, and then we need to figure out the internal force. If we have the internal force in the AB section and BC section, and we have the diameter of the AB section, BC section, we have the area, then we can calculate the stress, and that one should be lower than allowable stress. And then we can calculate this part is a function of D, and we can calculate what's the minimum D. From the big picture, makes sense or not? Okay, so let's say our goal is to make sure that for each section, the N over A, this one, which is the normal stress in the structure of each section, should be lower than allowable stress. So now for each section, our job is to find what is the internal force in the AB section, what is the internal force in the BC section. Let's start from the AB route. For the AB section, what is the internal force? What is the N here we should use? What's the internal force? Of course, there's only normal force. There's no shear. There's no bending. Bending and shear, that's 0. Only normal force. What is the normal force generated?
60 kilonewtons.
Yes, thank you. What is the internal force in this section? In BC section.
250 kilonewtons.
Sorry?
Is it 250 kilonewtons? Or
Uh,
just 125?
Think again. What is the internal force? Let's say one answer is, did you say 250?
Yeah.
Any other opinion?
190.
190. Any other opinion?
Zero.
0. Any other opinion? What's the internal normal force in the BC section? I can give you a hint. You need to consider sign.
Would it
60.
be negative 190?
Yes, 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 yes. It should be negative because 250, 60. So in the end, it should be compressive 190 in this BC section. And we keep emphasizing that we need to put a sign convention because if you say 190, I would consider it's tensile. But the real situation here is compressive. So we always make sure that no matter for the internal force and normal stress, they're in the same sign convention. So if it's compression, we do need to put the negative sign. It should be negative 190. Let's since this is the first example problem, let's not skip any steps. I still do the free bar diagram for each section. So for the AB section, the internal force, let's use NAB. So this one is simple. NAB minus 60 equal to 0, NAB equal to 60, and we know this positive 60 means AB is in tension. And for the BC rod, we need to consider the entire, either entire left side or entire right side. So if you use the entire right side, you need character reaction force first. So let's do this. Now here I have normal force in the BC section. So we have positive MBC. And just 125 in the positive direction, 60 in the negative direction, and MBC equal to negative 190 kilonewton. Any question for this internal force in the AB section and BC section? Okay, now the rest part is simple. We just calculate normal stress in each section, right? So for the normal stress in the AB section, we can put as let's not skip any steps. AAB. So it's equal to 60. Let's convert all the, because dimension given as, well, this dimension, megapascal. Okay, let's use Newton and meter. Newton DAB squared. So now the unit, for the dimension for the diameter should be meter, because I convert everything to Newton meter. And megapascal I also converted to Newton meter, 10 to 6 Pascal. So DAB should be greater or equal to meter. So this is for AB section.
I have a question.
Yeah.
Can you just explain real quick? We're using the diameter at AB, and then plugging that into the pi r squared equation.
Yeah.
And then, so then why isn't that pi over 2 if the diameter is like divided by 2 equals the radius?
It should be.
I'm missing something like
Are you asking why it's 4 here?
yeah.
Because the equation for calculating the area of the circle is pi r squared. Now you have diameter. Radius equal to half of diameter.
Got it. Thank you.
Yeah. So this is for the AB section, and then for the BC section, the same. But the only difference here is that when we say allowable stress is 150, it means that if the tensile stress is greater than 150, it will fail. If the compressive stress is greater than 150, it also fail. So here, when we do calculation, we just do the magnitude. So we are comparing the magnitude for failure. But I do want to clarify here, in real situation, some of you from material science, so in real situation, a lot of times the material they can survive for higher magnitude of compressive stress than the tensile stress in real situation. But here this is simplified calculation problem. So we consider it fail at the same magnitude. So tensile 150 fail. Compressive 150 fail. Real situation may be different. The BC square, and this one should be lower than allowable normal stress. So the BC should be greater than equal to 40.
In the original problem statement, what was the units for what was given? Was that micropascals?
Megapascal.
Oh, mega, okay.
Yeah, so megapascal 10⁶ Newton meter square, Newton per meter square. Yeah, any question for this example problem? When it's compression, we take the absolute yes. Because that we are calculating diameter is always positive. So here we have the assumption that when it fail tension is 150, when it fail, because compression is also fail at magnitude of 150. Any other question? Did I answer the question? Diameter should always be positive. There's no negative diameter. Yeah. Okay. So let's move on to the next topic, shear stress. Shear is this situation. Let's say if I support on this side and this side, and this center part is not supported, and they apply a force on this transverse force on this unsupported section, it will generate shear stress at this surface and the opposite surface. So basically, you see the two surfaces with the tiny arrows on. The tiny arrow means the shear stress. So for calculating the shear stress, the equation is shear force. This is the shear force calculated from statics over the area. And one thing I want to emphasize, even though in the normal stress, we can safely assume that the normal stress is uniform distributed because the variation is very small, but shear stress, the variation is not as small as normal stress. So we cannot really say that shear stress is uniform distributed on these two sections. So that's why, let's say, at the early stage of mechanics material, just put an average here, subscript average. So tau average equal to the shear force, the internal shear force, whatever shear force calculated here, divided by the area. And this area, don't get confused of the area in the normal force and normal stress, because in the normal stress, we consider this area that is perpendicular to the force applied, right? This cross-section area. For calculating shear stress, it should be this area. So now you can see that this area is parallel to the force applied or parallel to the shear force. So this is a little bit different. Tau average, it's average shear stress. And we intentionally put the subscript average here because it's not uniform distributed over the cross section, over the section of the area. We'll talk about how it's distributed in detail in the later chapter. But here for now, we just use this one to calculate average shear stress. And V is internal shear force. It's whatever you learned from statics. A is cross-section area of this structure, but we also need to be clear that this cross-section area is parallel to the force applied. So this area is parallel to the shear force. And back here, the cross-section area here is perpendicular to our force applied. So this is a little different. So when we do the calculation, you just make sure what is the area you should use for calculating stress. sign convention here is same as internal shear force, for our mecast materials. You may see different sign convention later in the FEA class, but it's okay for this class. Just use the same sign convention. Mhm. And we also have for the shear force, remember in this example problem, I told you guys to, oh no. In the second example problem in the static review, I told you that there's a double shear and single shear, and I told you guys to ignore. But here, let's say now we do need to consider if it's single shear or double shear. So this is considered as single shear. And so in this situation, if you do the free body diagram, of course, the shear force, normally we put a V here. Some tests will use P, sometimes most of the tests will use V. The shear force equal to this F applied. But this is double shear situation. Now the shear force, since the shear force is on these two surface, two cross section, so shear force generated on this cross section is equal to half of the force applied. So this is a single shear and double shear. So when you calculate stress, of course, it will be different. For the single shear, tau equal to V of A, here equal to F of A. But for the double shear, you can consider the force F is carried by two cross-section area. So again, shear force of A you can either consider is a shear force half, or you can also consider it's same force but carried by two area. It's the same thing. Any question for this part? Any question for this class? So I think it's time. If no question, we are done for the class today. Thank you for coming and have a great weekend. If you have any question about the class and the homework, you can come to my office. I will change to the Zoom office or Zoom link. Thank you and have a great weekend.
Thank you.
Go back a little bit.
Thank you.
You're welcome. To where? To where do you want to see? At the end of the notes. At the end of the notes. Here? Okay. Is there any additional homework due on Mondays? No, since we didn't finish this topic today, so the homework related to this topic will be due on Wednesday. So
Sorry, will you still be posting homework 2 on the files?
posting what? Sorry.
Homework 2 on the files?
Yeah. I will post this afternoon.
Okay.
Okay, I will change to the office hours Zoom link. Have a great weekend. You're welcome.